All right, welcome everybody to our Summer of Powerful Learning session for today. We've got a great presentation on hand. Today's presentation is called Powerful Learning with Computational Thinking. And like I said, we've got a great session set up for you today. Let me take a minute just to introduce myself. My name is Todd DeSando. I am one of the instructional technology trainers here at Digital Promise with the Verizon Innovative Learning Schools. I'm going to turn it over to your two presenters for today, Kevin and Kelly, and let them introduce themselves.
Hi, I'm Kevin McElhaney. I'm a researcher in STEM and computer science education at Digital Promise. I was a former teacher. I taught math, physical science in high school for 5 years before doing research. I also want to acknowledge a few collaborators who are not in the session. Shatabdi, Gautam, and Cole are great collaborators on this project. Kelly?
And hey, everybody, welcome to our session. I'm Kelly Mills. I'm project director for computational thinking here at Digital Promise. And I was also a former teacher, a former high school biology teacher for 8 years before joining Digital Promise. So I'm really excited to be with you here today.
Excellent. Before we get started, we have just a few community agreements that we like to address before the session starts. It's just a couple of quick norms as we're heading into our time today. The first one, please make sure that you are keeping your mics muted. Use the chat feature if you have any comments or questions. And of course, we love those reactions as well as we're going through the session. Number two, and really it's the next two, they're a little bit more, as we say, meta. Please be mindful of why we're here today and the importance of why we are here, and be present in the moment. The session is only 60 minutes. So again, thank you for carving out that little bit of time that you have in your day to spend with us. And third, and this is perhaps the most important one, be kind to yourself and others throughout this entire process. And remember that we are all here because we want to better ourselves and we want to see change being made within education. And with that, back to Kelly and Kevin.
Okay, so we know that the overarching theme of these presentations is Summer of Powerful Learning, and one of the tenets of powerful learning is authentic and challenging. So let's unpack that a little bit. What does it mean to be authentic and challenging? To be authentic means that students need a purpose for learning that is meaningful and relevant to themselves. And then to be challenging means that teachers are their guides, have high expectations for them and have active support enabling them to engage in that productive struggle. So they're trying different things and trying different solutions themselves. Next slide. And so in this session today, we are going to be connecting computational thinking to powerful learning and specifically authentic and challenging instruction. We will explore computational thinking resources for teaching that you can hopefully use in your classroom. And then Kevin is going to guide us through a real-world computational simulation, which is a cutting-edge example of computational thinking that you might use something like this in your classroom. We're going to ask you to open the simulation on a separate tab right now because it does take about a minute to load. And so the simulation runs best on the Chrome browser, and you could just launch it and kind of set it to the side. I'm going to talk through a few slides and then we'll come back to it. So Todd's going to drop that link now. Thanks, Todd. Okay, our warm-up today is for you to describe your interest in or experience with computational thinking, but don't press send yet because we're going to do a waterfall. So compose a sentence or two in the chat that answers the question, but don't press send until I say so. And then everybody's responses will kind of populate the chat at the same time and we can read through them together. So I'll give you maybe a couple minutes to think about it, seconds, maybe 30 seconds to think about it and type your answer in the chat right now. Maybe 10 more seconds to finish up your last few words. Okay, send. All right. I'm going to read through these quickly, making things challenging for students interested in learning more about it, a background in mathematics, ability to solve problems in a variety of ways. I'm seeing a lot of problem solving. Some people have more experience than others, and that is totally fine. We do not expect anybody to have any experience at all. And so we're happy that you're here. And what I'm seeing a lot of people talking about is this kind of complex problem solving, and that's really at the heart of what computational thinking is. So I think everybody is here for the right reasons, and that brings us to our next slide, Kevin. So computational thinking is an interrelated set of skills and practices. And these are all related to solving problems and solving problems in systematic ways that are related to how computers to solve problems, or how humans might communicate with computers to solve problems, but not necessarily using computers. So it's a little bit complex. And it's definitely not just programming. So I think we'll learn more about it in our example that Kevin's going to walk us through later. And as soon as I'm done with these slides. So computational thinking leverages unique affordances of computers for solving problems, and computational skills are important for everyone to engage in our increasingly technological society, not just those that want to enter STEM or computer science, but really the computational skills are really pervasive in our workforce. So computational thinking is authentic and challenging. Or should be authentic and challenging. And it's authentic because computational thinking gives students sophisticated tools to engage with complex real-world problems. They enable students to conduct more sophisticated analyses of real-world data, or conduct more sophisticated predictive models of a phenomenon. In the second part of this session, Kevin will introduce a curriculum unit where elementary students develop a computational model that predicts the amount of water runoff that results from a given amount of rainfall on a particular surface material. And then students then use that model to help them solve a school's water runoff problem. And computational thinking is challenging because it integrates STEM practices such as analyzing data sets, modeling systems, and designing solutions. In applying computational thinking practices, instruction is student-driven. Students engage in STEM practices, generate their own solution, and create artifacts. In the water runoff unit that Kevin will speak about shortly, students must first understand how water runoff works, then write the computer code to model it, and finally use the model to test their own design configurations of school grounds. And if you want to learn more about computational thinking, we have this opportunity for you to explore more with our example lessons library for computational thinking. And Todd is going to drop that link in the chat. We don't have a whole lot of time right now to explore it, but we encourage you to explore it on your own time, maybe after this session. And I'm just going to walk you through what it is and how to use it right now. So it is exactly what it says it is. It's about 100 computational thinking lessons that some of them Digital Promise developed, but really from all over the internet, that we think are really good examples of integrated computational thinking. And when we say integrated, we mean that it's integrated into other disciplines. So computational thinking integrated into English language arts, or math, or science, all these other disciplines. And you can see that you can filter for those disciplines down on the right-hand column. So you can filter for disciplines that they're integrated in, also grade level. So you can look for lessons specific to the grade level that you teach, and then also the skills and practices that are highlighted. because as I mentioned before, computational thinking is an interrelated set of skills and practices which compose all of those things listed. Okay, so I believe the next thing is to do a little temperature check. How are we doing? So if you could drop in the chat a 1, 2, or 3 to indicate how you're feeling at this point. I know I just spoke through those slides very quickly, but if you're unclear about the affordances of computational thinking, put a 1. If you understand, 2, and if you could explain them, put a 3. And I totally understand, or we totally understand that, you know, some people are coming with more prior experience than others. And if you're one of those people that does not have a lot of prior experience, we would in no way expect you to be able to explain everything about computational thinking with a quick 10-minute overview. And so however you're feeling, that's okay. And then the second part of the session, hopefully I'll give you an opportunity to learn a little bit more. Okay, so let's see. I see a lot of 2s. 2s are good. Okay, well,
There's
great.
in there. And no 1 so far. 1 would be fine too, because you have the chance to deepen that knowledge in the second part.
Totally.
I think I'm up, right?
Yep, you're up, Kevin.
All right. So we thought it would be a really fun opportunity to engage folks here in like what's really a cutting edge project. This is something that's not in the lesson library that we shared with you, because frankly, it isn't yet ready for scale. It's kind of it's a research tool right now, but a really great opportunity for you to see something that's really in development and research. And if this is around the curriculum materials around the water runoff that Kelly was referring to. So in this case, the water runoff refers to a phenomenon where the ground surfaces, say around a school or wherever, they don't absorb enough rainfall. And instead of soaking into the ground, as they ordinarily would through urban development, the water stays on the surface, runs downhill, and collects, resulting in situations like this picture you're seeing here, where all the water collects in the area and really causes a lot of unpleasant consequences. So in this project, this is actually a 3-week project where students take multiple days to actually develop and test their own computational model of water runoff, right? So first they sort of understand how runoff works, be able to predict it, and they spend about a week developing a little program that they can actually use to predict water runoff based on the surface material and the amount of rainfall. And so this simulation that we built, it kind of maps onto this area of the school in Virginia. Students develop code, and the code goes into this 16 square simulation that we've built. And they use the simulation to design the school grounds and test their solutions. So we're going to jump into the activity right at this point after students would have created the computational model and would be then ready to use that model to solve the engineering challenge. And I'll do a demo of the simulation shortly. But first, I want to give some overarching sort of parameters for the design task that you're going to be engaged in. So your task is going to be to use the simulation to design and test possible configurations of the school that meet these criteria, right? So for instance, on usage, right, there's going to be 4 out of the 16 squares, okay, that we saw in the simulation. Okay, 4 of them are fixed because those are the school buildings. And then there needs to be at least 4 squares of field for which you can use grass or artificial turf. Needs to be at least 1 square for a playground. Okay, and for that you can either use wood chips or this expensive material called poured rubber. And then there needs to be hardtop, so three hardtop squares for parking and at least 2 squares for hardcourt play. And the available materials for that are concrete, typical concrete, or sort of novel permeable concrete. Other criteria are that, well, first of all, you want to minimize the amount of runoff for 2 inches of rainfall. You have a $750,000 budget. And then want to ensure that a significant portion of the school is accessible to people with disabilities. So there have to be at least 6 squares that are of an accessible material. Okay, and we have a document that summarizes these, so you'll have that at your disposal while you're exploring the simulation. Okay, these are the available materials that that you can use. It summarizes kind of what they look like. You know, how much do they absorb? Okay, better runoff, of course, is more absorbent materials. More of the water goes into the ground instead of staying on top, right? Some materials are accessible to people with disabilities, others are not, and then they vary in cost. And again, this is the unit that we've done with fifth and sixth graders. So at this point, now that you see the design parameters, I'm going to demonstrate real quick. And hopefully you've launched this and this is available in your Chrome browser. But this is what it looks like. And I've kind of populated this with an existing design, right? A bunch of concrete, a little bit of field, a little bit of wood chips, right? If I wanted to change the design, okay, when you launch this, it's going to be all yellow, and you just have to specify all these materials for the first time. But like to remove a material, I just click on it, and now it's ready for me to put something else. To put something there, I'm going to click on this, and then I'm going to choose a material, and it'll put that material in that square. When I'm ready to test it, I'm going to click this green flag. All right, this is based on the Snap programming environment, so this starts the program. So I click the green flag, it starts to rain. I get a little storm cloud, and it shows out of my 2 inches of rainfall how much was absorbed using these rain gauges and how much ran off. Right, and then I might decide I can improve on that design. Let me replace this concrete square with something else like permeable concrete, and then run it again. Right, and so you'll be doing this iterative process to get at the best design you can. This is the code that's being run. Normally students would develop this themselves, but you don't have to worry about this today. And another thing that's useful is if you go to the custom set of blocks, you'll see this little design history. Okay, if you click on it, you can see what tests that you've conducted. Right, it shows today's date, what the cost of your design was. Okay, notice by changing one of my concrete squares to permeable concrete, I was able to improve the runoff performance. Okay, so I had less runoff, but it was also more expensive, right? And it'll tell you, basically summarize. So this will help you compare your designs from one to the next. And again, this is available in the custom set of blocks. That's kind of the basics. And at this point, we'd really like to let you run with this for a little while. So I think we'll, once you're in there, feel free to post questions in the chat if you get stuck. If you ever get stuck and something happens that you don't know where you were in the simulation, you can always reload it and just start again. That'll be the surest way to get it working again. So with that, I think we're gonna sort of have individual time to explore the simulation. Again, your goal, let's see, when we come back, we'll see what kind of solutions people got, right? How much runoff were we able to achieve, the lowest amount of runoff, still adhering to these design criteria. So I think we're going to reconvene around quarter till. Okay? And one more thing, as you explore this, consider these questions. I'll leave these up here, right? Like, what was your decision process for what to change based on the information you got from testing, right? What do you see other benefits of using a simulation to actually design and test a solution as opposed to doing it by hand, right? And then we're also interested in like, what supporting features of the simulation did you find helpful for designing and testing, and are there other features that you think would be more helpful to have? Anything else before I let folks work for about 25 minutes? Anything from you, Todd? Okay, so we'll be here. We'll be monitoring the chat for any questions, and we'll come back soon. Good luck in your design endeavor. balance hearing from as many people as possible, which we'll need to do in the chat. We'll also make a little more interactive by getting 1 or 2 verbal contributions, maybe for each of these questions. First, everyone just type in the number. What was the lowest runoff you achieved for a design that met all the other criteria in terms of usage and accessibility and so on? Just type it in. Let's see the range of results that people got. And then while you're preparing to do that, let's also just get some responses to the first question. How did you decide what to change about your design? How did you go about like looking at a design, getting the number? You got cost, you got accessibility, you got a runoff number. How did you decide what to do next? All right, seeing some runoff numbers going in there. See, someone posted a little earlier. They got under an inch, I think. Someone get under like a 0.9 or something. They were seeing 1.3, 1.1. .8. Okay. Yeah, if you were in the low ones, then you did pretty well. And given more time, this is only 25 minutes. Students, this is again a 3-week unit for students. So great, thank you for those contributions. Can folks type in just a comment, one example of how you decided what to do next? And I'll highlight one, and I want to hear a verbal contribution too. But in terms of the trade-offs, right? Noticing, oh, I'm too much on this, but I have room on this. So trade one for the other. I really like that comment. Would someone like to unmute and share?
I'll share. I don't know if it really worked, but what I tried to do was to position the surface material that was less absorbent above the material that was more absorbent, because the school or the land is on an incline. That's what how I was interpreting that. But I don't know if that worked as well, because my absorption rate was, I'm sorry, my runoff was still at 1.3. So.
Did anyone try to switch the positions, like having the same squares, but just in different positions, and to see if that made a difference? And did it make a difference? To my knowledge, it did make a difference. So the same squares, but in different positions, gave a different runoff number.
A little in my case.
Okay. So that was one strategy. Yeah, I saw one other person say, you kind of hone in on one variable, like keep cost, right? Focus on cost and then change things around under cost, right? Or accessibility. You gotta have 6 squares, so there's no reason to test anything less than 6, right? Keep it around there. So yeah. Okay, let's I'll just go back to this concept of trade-offs. Okay, trade-offs are actually a featured concept as part of what it means to optimize the solutions. The way the NGSS, the Next Generation Science Standards, actually call out optimization as an engineering concept, and trade-offs are a prominent idea within that NGSS defined view of optimizing. So this is a really important way we engage students in understanding what trade-offs mean for engineers. All right, second question. What did people perceive as the benefits of using a simulation to do this, as opposed to say, doing it by hand. Maybe some posts in the chat, or anyone would like to unmute and share.
It was really awesome to have like real-time changes. It was really easy to just go ahead and switch things out and run the simulation again. So I think that's one of the biggest benefits versus like having kids build a model or things like that. You get to still see what's happening, but you get the ease of changing out things quickly.
That's great. That's one of the things I like about online engineering as opposed to physical building. A lot of people think of engineering necessarily as building with your hands. We view engineering more as a thought process, and having a simulation enables students to focus on the revision process. It's much more rapid feedback cycles on your design rather than having to do like one every 20 minutes or one every day. So a big affordance there. Any others that people, let's see, here's one, a better visualization, right? Yeah, water runoff is not something we could easily model physically of a school. So that's definitely an appropriate way to visualize the problem. Instant feedback. Something we emphasize, you know, the fact that you're doing something repetitive over and over. Computers are very good at that, following directions and doing the same thing many times over, much better than we are, and without errors. That's another thing. In demonstrating the affordances of this simulation, right? We have a teacher start to do the calculation by hand, and it becomes very clear it's onerous, and that we're likely to make an error in doing that. So computers are really good at doing those things better than human beings are. I love the comment on math. We, as a design group, we spent a long time trying to make sure that the level of mathematics needed to understand this was accessible to elementary students, right? You know, you notice if you look at the code, the math is fairly simple. If this is bigger than this, right, you either add or subtract things. It was quite an effort to arrive at a sophisticated simulation that didn't require advanced mathematics. Something we like about this. All right, just in our last 3 minutes, what supporting features of the simulation do you find helpful? And what other features would you find helpful that you didn't see in here? I noticed someone posted above the reset button, made it easy to just reset and run again. The design history, someone mentioned the design history as being helpful. What other features did you like or would you have liked? And someone can unmute and share on this one too. Oh, gamification. Thank you for mentioning that one. It is like a game. It's like get the best score you can. There can be an element of competitiveness, friendly competitiveness in a class, right? Who can get the best number?
I really enjoyed that you could just double click the boxes to reset things and change out your material, but being mindful of like, if I was an elementary kid, I ended up moving a box away from its square on accident. So I had to line it back up perfectly and making sure that the instructions were like clear. I almost had to think about rereading the instructions just so that I knew I was looking for the smallest number in runoff instead of absorption, because the first like 5 minutes I was flipped around on that. So before it's released, because it is such a gamified lesson, making sure that they have the clear objective.
Yeah, thanks for that. Yeah, I agree. We kind of put you in the tough position of dropping you 2 weeks into the unit where students would have already actually built that model themselves, done the programming, and understood the sort of the runoff scenario. So thanks to everyone for being willing to join in the middle of the movie, so to speak. Changing the viewpoint, that's a really interesting question. Yeah, we did sort of fix the view kind of diagonal with flow to the right. That would be I don't know how our technology team would respond to that, but it sure would be a great feature to be able to move it around. Looks like people found changing the materials to be fairly easy. To reset the gauges. Oh, okay. I like that suggestion. Yeah, in terms of you either have to reset everything or nothing. And that would be good for us to advance that. So these are really good suggestions. I think we're at our 5-minute mark, and I think Todd's gonna take it from here. So before Kelly and I sign off, just thank you everyone for participating in this. I really enjoyed seeing everyone work in this and getting people's thoughts.
Thank you, Kevin. If you could bring up just the next couple of slides for me, and I'll go through those. I'm going to put a link to the survey into the chat, so please fill that out. It helps to give our presenters feedback on their session. And if you had requested a certificate when you signed up, one will be sent to you through email after you fill out that survey. And then just to give you an idea of the next coming weeks, Kevin, you can go to the next one. We still have many, many sessions on tap. Again, all of these sessions are on Tuesdays. Back me up on that, Lucara, right? Every session is on Tuesday, beginning at 1 p.m. Eastern. So next week we are continuing on with coaching towards authentic and challenging instruction. And again, the same website that you use to sign up for today's session is used to sign up for those future sessions as well. And then the last bit of information is on the next slide, and that is just a link to our VILS HQ. So Kevin, if you can go to that one. Okay, this is our Verizon Innovative Learning HQ portal, which is verizon.com/learning. And there are all different types of resources there for you, including professional learning and AR and VR apps and lesson plans and many, many more things as well. So just to echo Kevin and Kelly, again, I want to say thank you for giving a little bit of your time up today to join us. And if we could, either a reaction or on your camera, give your presenters a little bit of a round of applause on a job well done today. All right, and with that, we will see you during the next session. So thank you, everybody, and have a great rest of your day.